Hi, welcome to this video. Today I'm going to try to simplify circuit analysis, the basics at least. These are the sort of things that I found most frustrating and annoying in the start of my studies. I am currently studying electrical power engineering, so I've been through loads of circuit analysis. And what I found most annoying was the fact that we had to sort of remember loads of formulas and stuff. Things like the voltage division law, which was like V2 equals V in times the resistance over the added resistance, and it just gave me absolutely no intuition as to what was happening or anything. So we're gonna remove that. We're gonna go back to basics. We're going to derive things from scratch, things that are very easy to do in an exam setting, so no need to remember formulas and stuff like that. So what we're going to use today is just going to be Ohm's Law. So that says that V equals R times I. We're going to be using Kirchoffs Voltage Law. And we're going to be using Kirchoffs Current Law. Now, the voltage law literally just says that the voltage generated in a loop must equal the voltage used in that same loop. So if you've got, for example, a generator and a resistance here, so this is generating power, this is using power, the voltage generated here must equal the voltage that drops over there. That's the Kirchoffs Voltage Law, KVL. And the current law, if we extend this, current law says that the voltage in any branch, the current in any branch, so this will be I1, this is I2, going this way, and then I3 will be going down here. And the voltage going into a node must equal the voltage going out of a node. And as you can see, two of these voltages, so I'm saying voltage, I mean current. So the current going into a node must equal the current going out of the node. So as you can see, one current is going in and two currents are going out. So that means that the current going in must equal the currents going out. Okay, simple. They're the three things we're gonna be using, those three identities today, and that's basically all. So first off, I'm just going to define how we find parallel resistances. So I use this rule here. I do just remember this, but you can easily derive this from the definition, which is just by multiplying the entire thing by R parallel, then dividing it once by R1, and then again by R2. Multiplying by R1 and R2. You'll then get R1, R2 on this side, and then you'll divide by R1 plus R2. So you'll be left with this identity, and you can derive it in about 3 lines. So, and as you know, R series equals R1 plus R2. So you just add them together. So this is what we're going to be using today. Now we're going to be starting off with a circuit, which some people might find problematic. So we're going to have 2 loads in parallel and then another one in series with the parallel. So we'll say that the voltage here equals 100 volts. This is R1 and it will equal 10 ohm. R2 will equal 5 ohm, and R3 will equal 2 ohm. And we know that this voltage source here will generate a current that will travel this way. It will go through this resistor, but as we know, the current does not change through a resistor. It stays the same. The voltage is what changes. So the current on this side is exactly the same. It's still just I. We can actually call this I1. And then the current will split. We've got I2 going down and I3 going over here. And what we saw earlier was that from the Kirchoffs Current Law, that I1 equals I2 plus I3, literally because the current going into a node, or a point where an intersection point, has to be the same as the current flowing out of that same point, because there can't be you can't accumulate current in a point. It needs to leave it, otherwise you'd have a huge problem with your circuit, right? So the current leaving must equal the current entering. That's what this says. Pretty simple. So what we're going to do now is we're going to combine these two using this. So we're just going to say that R parallel will equal R2 times R3 over R2 plus R3. Hey, it's just that. Instead of 1 and 2, we've got 2 and 3 because that's what we call them. Now let's just input the numbers. So it's going to be 5 ohm times 2 ohm over 5 plus 2 ohm, which will equal, well, approximately equal 1.428. Sorry, we'll actually say 429 ohm. Yeah, so that is the total resistance in the parallel. So that is these two combined. Now let's just draw up the new circuit with this parallel. So since we've calculated a new value for the total parallel, we can just merge them into one. And that one, this one, will equal R parallel. And this is still R1, this is still V, and we've still got exactly the same current running through. The current runs all the way through, it's just I1, because now we've combined these two, so the current running through here will now just be, they won't branch off anymore. This branch has been hacked off and we've added them together. So it's just I1 throughout now. That simplifies it a lot. And now let's just add these two series connected together. It's obviously just adding them together. So the R total will equal R1 plus R parallel, which will just equal, what was it, 10? Yeah, that was 10. 10 ohm plus 1.429 ohm, which will equal 11.429 ohm. That's the total resistance in the circuit. And then we can obviously just simplify the circuit one more time. You don't need to do this every time. It's just to show you how we are simplifying this this circuit. So this is now R total. Still exactly the same voltage, same current. And now, since we've got this R total and such a simple circuit, we can actually solve for I1. So by using ohm, we know that V equals IR. This means that I1 will be V over R total, which is 100 volts, which is what we defined as, divided by 11.429 ohms, which is approximately equal to 8.74750 amperes. Yep. So this is now the current running through, the main current running through the circuit. That's the current that's being emitted by the generator. Let's draw up our original circuit again, a bit more properly. The intermediate steps, I like to draw the circuit pretty quickly, just very crude drawings, but when I draw up the full circuit I like doing it a bit more properly. So this is still V, this is R1, R2 and R3, and what we've found now is I1, which is the same here, I1. Now, in a normal sort of circuit analysis task, they might ask you, what is the current running through this branch, which we'll call I2. Now, I'm going to show you how you might go about finding that without using any formulas. We'll do it from scratch. Now, we know from the Kirchoffs Current Law that I1 is equal to I2 plus I3. And if we want to find I2, if the task is asking us for that, what we do is we just move it over. So I2 will then equal I1 minus I3. So we just moved I3 over. And we already know I1, and that's 8.75. So what we want to find now is I3. Now to do that, to find I3, we are going to introduce a new way of looking at the circuit. So we're going to use Kirchoffs Voltage Law. Now, Kirchoffs Voltage Law kind of works like, if you think about this circuit as two very separate and isolated parts. You've got one part there, and you've got a second part here. They are isolated. So what we're going to do is we're going to think about this in a circular motion. We're going to move around like this. And it's the same principle in both cycles. It's the same principle on both sides, but they are separate from each other. So we can choose. We can do it here, or we can do it here. The easier one in this case might actually be doing it here in number 2. This will be number 1. This is number 2. And it's a bit easier because we don't actually have a we don't actually have a voltage generator in this one. So the total voltage will be 0. We write KVL. Let's write KVL 1 because just a symbol, 2. To symbolize that we're going to use this node. So we'll write 0 because there is 0, and there's 0 voltage being generated here. There's just 2 resistors. And that is going to equal, let's begin on the left side. Now we've decided to go around this circuit in this fashion, so this way. That means that we're going to go up through this resistor. And when moving up through that resistor, we're going to meet I2 in the opposite direction, which means we just have to turn I2. So it's going to be minus I2 times R2 plus, since we're now moving with I3, we're going to go into R3. So I3 going into R3. Okay, and as we know, I2, as expressed here, can be changed into minus I1 minus I3 times R2 plus I3 R3. Okay, now we can just, we can multiply this by both these values, and remember the negative sign is very important. So 0 will equal minus I1 R2 plus I3 R2. So the plus is because we've got two minuses, so it becomes plus I3 R3. Now, as you can see here, we know every value except for I3, so we can solve for it. We'll just quickly move out the parentheses. Okay, then we'll move this to the other side. Got I1 R2 equals I3 times R2 plus R3. We'll just divide quickly by R2 plus R3. Right, just to move this over so we can solve for I3. So I've divided and I've just sort of flipped it because I want the answer on the left side. That's just convention. You can of course just write I1 R2 divided by R2 plus R3 equal I3. I just like it the other way around. Means exactly the same. There we go. Now, what is this? Is this not exactly what the current division law is, where we put I1 R2 over R2 plus R3? Yes, that is exactly what the current division law is, the one that you're always said to remember. But we don't need to remember it. We can do it. If you understand the circuit properly and how it works, you can just get to it without having to pain yourself through remembering these formulas. Just understand it and do it. Now, let's solve for I3. It will equal I1, which was, let's go up and see, 8.75. Remember that these are approximate values. Times R2, and R2 was 5 divided by 5 ohm plus the last one was 2, I think. It was 2. Let's solve that. So that will equal 6.25 amperes. So that means that 6.5 amperes out of the total 11 point something is running through branch number 3. Now, we saw that KCL said that I1 would equal I2 plus I3. We now have both I1 and I3, so we can solve for I2. Simply I1 minus I3. And I1, let's check what that was again. 8.75, of course it was. Minus 6.25 will equal 2.5 amperes. So 6.25 amperes, if we draw up the circuit again, so that is 8.575 amperes, 2.5 will run down there, and 6.25 will run down there. They're all in amps. Now, what can we use this for? Well, you can find the voltage drop from here to here, from here to here, from here to here now, because you've got the current and you've got the resistance. So this is R2. If you want to find the voltage drop over R2, you'll just write V equals I2 times R2, which would just be 2.5 amps multiplied by, was it 10 or was it 5? I think it was 5. Let's say it was 5. Sorry, 5. That is 12.5 volts. So the voltage drop over this is 12.5. Let's find the voltage drop over that one. So that, we'll call that V2, V3. So V2 is here, and V3 is here. That's I3 times R3. That's going to be 6.5 amps times 2 ohm. Sorry, it was 6.25. And what do you know? 12.5 volts. They're the same because the voltage is the same in the parallel. That's what we know. When you've got a parallel connection, the voltage stays the same. In a series, it will not be the same, obviously. So we can find the voltage drop over the large, the 10 ohm one. So V1 is I1 times R1, which will be 8.75 amps times, what was it, 10, which is 87.5 volts. And what is 87.5 plus 12? Well, it's exactly 100, which was our generation voltage. Because these added together shall become the complete voltage drop, because there is no extra voltage drop when you've got a parallel. It's just the same. Yep. So I hope that made some sense. If there's anything else you'd like to know, or anything you'd like to be made clearer, please let me know, and have a great day.